Newton's method. Newton's method is an algorithm for computing increasingly accurate approximations to a root of a function. That is, a solution of an equation of the form f of x equals 0. Of course, we can think of the root of a function as the x-intercept on the graph of the function. The idea is to improve a given approximation by computing the root of the linear approximation there, and then to repeat that process until the desired accuracy is achieved. So, for instance, suppose we have a number x0 that's reasonably close to the root that we're trying to compute. The tangent line at the corresponding point is the graph of the linear approximation at x0. That tangent line crosses the x-axis at a number x1. This is our improved approximation. Now we basically repeat the same process. The tangent line at the corresponding point is the graph of the linear approximation there. It crosses the x-axis at some number x2, which hopefully is an even better approximation than x1. So let's see how these computations should be done. Let's write the linear approximation to f at x0. Y equals f of x0 plus f prime of x0 times x minus x0. We set y equal to 0, and we set x equal to x1, and now we want to solve for x1. x1 minus x0 is equal to minus f of x0 over f prime of x0. This term is sometimes referred to as the Newton correction, and so x1 is equal to x0 minus f of x0 over f prime of x0. x2 is computed from x1 using the same formula, and so on. And in general, we have the formula x sub n plus 1 equals xn minus f of xn over f prime of xn for all integers n greater than or equal to 0. Example. Let's use Newton's method to compute the square root of 3. First thing we have to do is cast this problem as one of finding the root of a function. The key here is to notice that the square root of 3 is the positive root of f of x equals x squared minus 3, whose derivative is just 2x. So now let's write the Newton's method formula for this particular function. xn plus 1 equals xn minus the correction term with numerator equal to f of xn, that's xn squared minus 3, divided by f prime of xn, which here is 2 times xn. Notice that if we break up the fraction here into two parts, the first term is 1/2 xn, and the second term is 1/2 of minus 3 over xn. So this simplifies and becomes xn plus 1 equals 1/2 of xn plus 3 over xn. So now the question is, what's an appropriate choice for our initial guess x0? Well, we know that the square root of 3 is between 1 and 2, since 1 squared is 1 and 2 squared is 4. We also know that the square root of 3 is greater than 1.5, since 1.5 squared is 2.25. So why don't we just try x0 equals 2 and see what happens? We'll indicate here how this computation can be done on a typical calculator. We'll first enter x0, our initial guess, and then we'll enter the Newton's method formula using answer to refer back to the previous calculation wherever xn appears. Now we press enter to calculate x1. Pressing enter again gives us x2, and we continue to press enter to get x3, then x4, and then x5. We now notice that x4 and x5 are the same. That is, these are approximations to the square root of 3 that agree to all of the digits shown. So as far as our calculator is concerned, we have now calculated the square root of 3. Now let's check by squaring the result, and we obtain 3 as we should. Example. Find the 3 points where the graph of y equals 3 minus x squared intersects the graph of y equals 1 over x. Here's the graph to illustrate what we're looking for. Notice that there are, in fact, 3 points of intersection. As usual, when we look for points of intersection, we'll set the two functions equal to each other. Here we have 1 over x equal to 3 minus x squared. Solutions of this equation will be the x-coordinates of the points of intersection. Let's multiply by x and rearrange so that we have 0 on the right-hand side, and we now have the problem of solving the equation x cubed minus 3x plus 1 equals 0. This is a root finding problem where the function is f of x equals x cubed minus 3x plus 1, whose derivative is 3x squared minus 3, and so the Newton's method formula can be written as xn plus 1 equals xn minus xn cubed minus 3xn plus 1 divided by the derivative at xn, 3xn squared minus 3. So let's begin by trying to calculate the leftmost point of intersection. From the graph we can see that the x-coordinate is approximately minus 2, so let's use that as an initial guess and begin by entering that in our calculator. Now we'll type in the expression on the right-hand side of the Newton's method formula using answer in place of xn, then enter to calculate x1. Then we press enter again to get x2, again to get x3, and then again to get x4. Notice here that x3 and x4 agree to all but the last digit. This indicates that x3 is accurate to all of those digits of agreement, and so x4 is likely accurate to all the digits shown. Since we want the corresponding point of intersection, we'll just calculate 1 over x4 to get the y-coordinate of that point of intersection. So here are the coordinates of that point written out to 6 decimal places. Now let's try to find the point of intersection in the middle. The x there seems to be somewhere around 0.5, so let's use that as an initial guess, x0, and again enter our formula exactly as before. Press enter to compute x1. Then we continue pressing enter to calculate x2, x3, and x4. Again, notice that x3 and x4 agree to nearly all digits, all but the last two, and so x4 is likely accurate to all of those digits shown. Now we calculate the y-coordinate, 1 over x4, and so to 6 decimal places, here is that point of intersection. Now let's calculate the third point. The x-coordinate there appears to be near 1.5, so let's use that as x0, enter. Type in our formula again, press enter to get x1. Then continue pressing enter. And notice here that x3 and x4 agree to all the digits shown. The y-coordinate is now 1 over that result, and so we have now found the third point. Notice that the same Newton's method formula was able to compute 3 different x values due to the different choices of x0. Another example. The length of a circular arc between points P and Q is 210 feet. If the straight line distance between P and Q is 200 feet, find the radius of the circular arc. Let's begin with a diagram. Here are points P and Q. Here's a circular arc joining them. This has length 210 feet. The straight line distance between P and Q is 200 feet. Now let's draw a segment from each of the points P and Q to the center of the circle and label the length of those r. Now let's notice that if we draw a horizontal line through the center, we then have a right triangle whose altitude is 100 and half of the circular arc has length 105. Now let's let theta be the angle that's opposite the side that has length 100. And now we can write down 2 things about the angle theta. First, the sine of the angle is 100 divided by r. That's opposite side over hypotenuse. Also, by definition of radian measure, theta is equal to the length of the subtended circular arc divided by the radius r. Let's substitute that second equation into the first and write sine of 105 divided by r equals 100 divided by r. Now let's simplify this a little bit by making a substitution. Let's let 105 divided by r equal x. So the left-hand side of the equation is simply sine x. And let's notice that that's equivalent to r equals 105 divided by x. The right-hand side, 100 divided by r, will equal 100 times x over 105, which is the same as 20 over 21 times x. So with these substitutions, the equation becomes sine x equals 20 over 21 times x. And of course, we can multiply through by 21 to obtain an even simpler equation, 21 times sine x equals 20x. So this is the equation we'd like to solve. Once we solve it for x, we'll then use the equation r equals 105 divided by x to find the radius r. So to find a solution of our equation, we'll use Newton's method, and so we need to recast this as a root finding problem. We let f of x equal 21 sine x minus 20x. The derivative is 21 cosine x minus 20, and so the Newton's method formula is xn plus 1 equals xn minus f of xn divided by f prime of xn as usual. So now let's do the calculation. We first need to find a reasonable value for x naught. To do that, we can graph f of x. This graph is on the interval 0, 1. It indicates an x-intercept that's a little bit to the right of 0.5. So let's use 0.5 as our initial guess x naught. So now let's type in the formula, press enter to calculate x1. Now we press enter again, and we have x2, and then again to get x3, and so on. And now we notice that x4 and x5 agree to all the decimal places shown. Now we go back to the formula, r equals 105 divided by x to calculate the radius, and we find that it's very close to 195 feet. One more example. Find the minimum value of the polynomial f of x equals x to the 6th minus x squared minus 40x. Here's the graph of the function. Notice we're looking for a minimum that occurs at a critical number that's in the vicinity of 1.5. That critical number will be a root of the first derivative, which is 6x to the 5th minus 2x minus 40, which after factoring out a 2 becomes 2 times 3x to the 5th minus x minus 20. Now, to use Newton's method to find a root of f prime, we need to calculate f double prime. That turns out to be 2 times 15x to the 4th minus 1. And so the Newton's method formula for finding a root of f prime is xn plus 1 equals xn minus f prime of xn divided by f double prime of xn. And notice that we can dispense with the factors of 2 in the numerator and denominator. So now we're ready to do the calculation. Let's use 1.5 as our initial guess. And now we enter the right-hand side of the Newton formula. Press enter, and we have x1. Now we repeatedly press enter, calculating x2, x3, x4. Notice that x3 and x4 agree to all the digits shown. Therefore, that's a good approximation to the critical number we're looking for. Now we calculate the value of the function there, which turns out to be roughly negative 50.88. The Newton's method theorem. Suppose that f of r is equal to 0, that is, r is a root of f, and that f prime of r is not 0, and f double prime is continuous on an open interval containing r. If f naught is sufficiently close to r, then x1, x2, x3, and so on become successively closer to r. Notice the very important condition here that says if x naught is sufficiently close to r. In fact, in many problems, x naught must be very close to r in order for Newton's method to work. Also, there's a constant c such that the absolute value of xn plus 1 minus r is less than or equal to c times the absolute value of xn minus r squared for all n greater than or equal to 0. Notice that this says that the error in xn plus 1 is less than or equal to a constant times the square of the error in xn. So, for example, if xn is within 10 to the minus 3 of r, then we expect xn plus 1 to be roughly within 10 to the minus 6 of r. This tells us that the error decreases very, very rapidly once the error becomes small. In fact, a good way to think about this is once we're close to the root, the number of decimal places in our approximation roughly doubles at every step. This is often called quadratic convergence. Let's look at an example to see how this works. The Newton formula here, which we would use for finding a zero of the cubic polynomial x cubed minus 3x plus 1, produces this table of numbers, starting with an initial guess of 1.5. Here, the calculations were done with 100 significant digits, and each of these numbers is shown out to the 92nd decimal place. The last number here, x7, is actually accurate to all the digits shown. Now let's compare that with each of the preceding approximations. 1.5, our initial guess, is accurate to 1 decimal place. x1 is accurate to 2 decimal places. Now comparing x2 to x7, we see that x2 is accurate to 5 decimal places. Notice that the 5th decimal place is actually different from the 5th decimal place of x7, but if we rounded each of those numbers to 5 decimal places, they would be the same. Now comparing x3 to x7, we see that x3 is accurate to 11 decimal places. Comparing x4 to x7, we see that x4 is accurate to 22 decimal places. Now x5 is accurate to 45 decimal places. And finally x6 is accurate out to 91 decimal places. So notice how the number of correct decimal places roughly doubles with each step.